sound waves in confined active liquids. And this is work done with a very talented postdoc who led the theoretical part of the study, whose name is Anton Suslov, a very good PhD student responsible for most of the numerics. Denis Barthelot, who is a long-time collaborator at the University of Lyon, and Alexandre, who is in the audience, who is responsible for some of the preliminary experiments that I'm going to be showing. And before we move further, I would like to tell you what a topological sound wave actually is. This is not a concept that is very familiar to our community. In fact, the concept of a topological sound wave, starting in the concept of a topological excitation, what sometimes is called the chiral edge mode, started in the physics of the quantum Hall effect, the integer quantum Hall effect, is very familiar to people who study topological insulators. So you may think it's not a terribly appropriate topic for this conference. But what has happened in the last few years is that several people have been busy exploring the connection between these ideas that originated in the physics of electronic system in the context of phononics, or if you like, acoustics, mechanics. Okay? And there are many suggestions in recent time on how to use the principle of topological protection in acoustics. And to make sure that it's clear what a chiral edge wave is, I want to show you an example of that. And hopefully, by just looking at the phenomenology of this example, you can decide yourself whether you're interested in or not from the perspective of soft matter physics, mechanical engineering, without caring that this maps to exotic topics in quantum Hall physics. And I'll do so using an example which is actually an experiment or a prototype which has been actually built in the lab of William Irving at the University of Chicago. So let me tell you what you're looking at. What you're looking at is an example of what some of us would call a metamaterial, which means a structure which has a unit cell which is a bit funny. Funny means it can have some interesting geometrical properties, as we'll hear, I think, in the talks of Brian Chen and Zed Rockley, or it could have another funny property, which could be a material that breaks down universal symmetry, which is what's going to happen here. So what you're looking at is a bunch of gyroscopes, which are hanging and they have inside a motor that keeps them spinning. At the same time, these gyroscopes are coupled by, well, magnetic interaction in this case, but they could be coupled with springs. And so the question is, if you probe this system at a special frequency, the following happens. And I should say, this is work done by Lisa Nash, Dustin Kletchner, Alice Nari Reed, Ari Turner, who is one of the leading experts of topological insulator of the new generation, and of course William, whose lab has been engineering the structure. So, but without distracting from what happens, let me tell you, imagine that you're poking at the edge of the system at a given frequency. So you spray with a given frequency. A frequency that corresponds to a gap in the spectrum of this structure. What you'll see is the following. A wave in the face of this, of the tip of this gyrus will start propagating. But the peculiar feature of these acoustic waves is that it propagates only at the edge. It doesn't enter the bulk, aside from a small imperfection due to the fact that this system is not ideal. And as, of course, it moves at the edge, you may ask, well, okay, that may be interesting, but why is it so important that this wave moves at the edge? I mean, you can organize an excitation to be localized at the boundary using various strategies. Why is this special? Why all this big fuss, and why is it topological? And the answer is, it's not so much the fact that these things move at the edge, as what happens when you disturb the edge, which is peculiar. In particular, what happens is, as the experimentalists did, you put an obstacle in this material, but literally removing some gyroscopes. So this is no longer an ideal structure. And you repeat the same experiment. Now, if this was a normal wave, as it hits the obstacle, it will scatter. Whereas I want to show you what this special wave does. The special waves start here, and then goes around the obstacle. Okay? Returns here, and it keeps moving around. Of course, if this was even bigger, you would see it even better, because the penetration depth here is quite big. Okay? So if you put imperfection at the edge of the sample, the wave just goes around it, immune to the presence of disorder. And the reason why this has become very quickly a topic at the interface between theoretical physics and engineering is because there are many people interested in making materials or structure that propagate sound, so they are waveguides, immune to disorder and immune to imperfection. If you like, this is the ideal channel. Okay. Other questions as to what you saw? Now,
yeah, good question.
Yeah.
Why is it going one way the other way?
Very good. The other aspect is that this wave is unidirectional. This unidirectionality is picked up by the fact that each of those gyroscopes knows as a chirality of its own. Okay? But it's even more intriguing than that. It can be tuned by changing also the geometry of the lattice. That's why these things are called metamaterials. They're robust in some way, but they also have an element of tunability, as you can tune the penetration depth. And this is just an introduction to give you a visual of what the phenomenon is. Now, as you can see here, there's a lot of items on this list. One of them also includes two examples that have to do with fluids. You take fluids, and you put some spinning particle around them, and you can study waves in the system. This is a proposal. These two are theoretical work. This is an actual thing where it's been realized. Another proposal comes from the lab of Andrea Alou. If you take normal air, so this is a simple fluid, and you stick it inside this pattern of tubes, and you put at the node of this metamaterial a rotator or a circulator, which will circulate the air to keep it flowing, then you can realize in this structure also this topological sound waves. Now, the aspect I would like you to take away from this slide is that all of these systems are driven. So you need an input of energy, either in the form of the circulator or the battery that is in the gyroscope. Okay? And also you have to very carefully arrange the geometry of the structure. Okay? Partly because this is what happens with metamaterials. They're not natural structures. Hopefully they can achieve some functionality which is useful. Now, the question that underlies this talk is, can we get one of these topological metamaterial that displays this robust sound wave by self-assembly, rather than putting together gyroscopes that are machined, put them on a precise lattice? We want some components that are smarter, that will ensure the presence of a spontaneous flow without us having to engineer a circulator at each node of our material. Okay? And to have this perpetual state of motion, which is the first step in realizing one of this material, we're going to use metamaterial, which instead of being stuffed with air, are stuffed with self-propelled particles. Okay? And we're going to use the spontaneous flow as a key ingredient. Now, let me just tell you in a snapshot what is the central idea of this work. This is some unpublished work that's still not complete. So the idea here is the following. Imagine taking a container. This container will be formed of rings. There will be many more. We'll make a whole lattice of it. These rings share some region in which they will interact. And you stuff this ring with self-propelled particles. You're doing a microfluidic experiment inside the confined geometry, suitably shaped. This is step one. And of course, you have to determine a suitable state of spontaneous flow. Step two would be to do an acoustic experiment inside of that structure. You'll have to look at the density waves. The way we're talking, actually, it's mostly me talking to you, is via density waves in the air that separates us. Here we're going to be studying the density waves in the density of the self-propelled particles. Okay? And I will show you how you can achieve these topologically protected waves using this technique. Okay? So to do that, I'm going to start doing it step by step. Now, it's not particularly crucial how you realize your model of self-propelled particles. In fact, some of our calculations are done in the continuum theory, but I think it's useful, at least for me, to be concrete, to start with something microscopic. Okay? And so there are many models of self-propelled particles. Some of them have the advantage that you know how to coarse-grain them very well. One of them is the Vicek model. But there's also this other model that we've been studying, introduced in this reference. Now, this model is a little bit less standard than Vicek, so I'm just going to go through a description of what it is, although it's essentially what Itai discussed this morning. So, first of all, what the variables means. X is the displacement of each of the particle. I labels each particle. The acceleration term in this equation is completely useless because we can work in the overdamped limit. But I'm going to walk you through all the other terms. First of all, this one in particular is a short-range repulsion that will prevent, for example, an exponential, some Yukawa interaction, that will prevent this particle from clamping. If you wanted to do this with the Vicek model, you have to do it at finite temperature. Okay? Otherwise, they will clamp. The second term that we put, it's an alignment term. So x dot with an at, which is just the unit vector, the speed, this term means that all the velocity of the particle want to align in a common direction. This is like flying spin, sometimes called. The second model, the other term is an active force. This is the most important of all. There is a force of magnitude F naught that acts in the direction in which the particle is moving. Remember, this is the unit vector of speed. Okay? And the third component is a drag. There's dissipation, Stokes drag. And so, the crucial point is that if you took a ring and you stuff with these objects, pretty much irrespective of all of these details, there will be a circulation developing. Okay? And the amplitude of that circulation, if you like, the speed at which it moves, is given roughly by the ratio between F naught and gamma. Will depend also a little bit on the density, obviously. I mean, if the density is too high, you just get stuck. That's why for us it was important to have a microscopic model, because the getting stuck is hard to get from the Turner-2 equation. But it's important if you want to make a device. Okay? Now, and of course, the circulation can be either clockwise or counterclockwise. This is an example of spontaneous symmetry breaking. And in this talk, I'm going to denote red and blue to denote the two cases. So this is a map of the circulation, if you like. Now the question is, what if these rings are not just such a simple geometry, but something more complicated, like this, for example? Well, now you know there's going to be this region in which the particles that are coming from here and the particles that are coming from here interact. And what this term will want to do is to want to make them align in the same direction. That means that when you have two of such rings connected to each other, sharing an area, then there will be a propensity to develop what you could call an antiferromagnetic order. In other words, one ring has to go counterclockwise, and the other one goes clockwise, or vice versa. This is favored energetic. Okay? This is pretty intuitive, and I think it's demonstrated and demonstrable, as I'm going to show you with experiments. What we want to do is something a touch more complicated. We want to engineer lattices. And these lattices, and I'm going to give you a prescription on what choices of this lattice you have to make in order to reach this goal of the topological sound waves. This is an example of a Lie lattice. Now in this lattice, again, it's filled up with this particle, self-propelled particle, and the unit cell of the lattice is this 3-ring unit cell. This is shown with periodic boundary condition. And as I said, intuitively, we expect counter-rotating, rotating, so this alternating pattern of rotation and counter-rotation. Just as an illustration that this is indeed intuitive, we performed some simulation. This looks like a mess, but after a while, the mess approaches a steady state. Okay? Let's see if you can walk with me. Here, can you see here that it's going clockwise? Here is going counterclockwise, and here is going, again, what is this? Counterclockwise. So this is exactly the alternating pattern of circulation that I illustrated in red and blue here. Is this clear? So, this is an illustration which was constructed using the simple model that I showed you, the simple numerical model I showed you. But it can be done also with real active fluids. Alexandre, who is in the audience, is an expert in this system, which was engineered in the in the lab of Dundee, which are these rollers. So what they did is stuffed. This is slightly different microscopic realization. In fact, even at the level of coarse grain, it is not equivalent to the previous one. But what you can see here is that they stuffed these rings with this fluid, and the metamaterial is exactly composed of that. And when you look at it, you can see what you expected. See, here is the region where they share particles. So here is going counterclockwise, here is going clockwise, here is going counterclockwise. This is a zoom in of that very complicated mess. And what this realizes, if you like, is this circulation map. Okay? And you can ask Alexandre about the details of his rather sophisticated experiment. Now, I will stick for the rest of this talk to the simple realization that pertains to the microscopic model presented in the first slide. Although, I mean, we're working closely with them to develop the theory also for their experiment, which is a touch more complicated. Now, there's one thing that I want to tell you. This collective motion, which is induced by the boundary and the activity, which is a universal feature of active matter, which we certainly have not discovered for the first time, it's not the topological edge current or the topological edge mode that we're after. This is just the first step. In fact, if you want an analogy with this system, this step here corresponds to having gotten each of the gyroscopes spinning around its axis. But here is done, of course, by self-assembly and with a lot of particles. What we have to do now to do the equivalent of this excitation that moves around the edge when you poke the system is to apply a perturbation to this system. And in particular, we have to study acoustics, or the sound waves that exist on top of this flow path. And I'm going to tell you why the choice of the lattice, for example, is so crucial, and why you have to solve the self-assembly problem carefully. You see, if this was a simple fluid, you can just put a drive that does what you want. Here is the geometry that chooses at the interplay, of course, with the fluid. So, one of the advantages of working with the models that you know what they coarse-grain to is that once you determine what the spontaneous flow, the state of spontaneous flow is numerically, and the condition within your microscopic model, pick up the one that is more suitable for you, such that there is this steady state, then if you want to study the acoustics on top of that steady state, you don't have to do it necessarily by simulations. You can then do it with a, if you want a pretentious word, what is it, hierarchy, I mean, what can I not say? Just you do some part in simulation, and the other part you do analytics by sticking, what's the name? Yes, on the hybrid. There's one which is even more fancy that I prepared to say, but I can't remember. Multi-scale. Multi-scale. That means you know essentially you do whatever it is in one way, whatever it is in the other way. And now, to study the sound waves, once you know that there is this edge, this steady state, you can go to the suitable hydrodynamic description of this model. This was that model essentially coarse-grained to a model, one of the first models active matter by Turner and Two. There is a lot of interesting background for those who are not familiar, although this is probably less relevant for this conference, in this review of modern physics by Christine and her collaborators. I must say, one of the things that I like the most about active matter is when one actually coarse-grains microscopic model and actually derives the continuum equation. Okay? For example, for Vicek model, you would not have to do it for some special choice. For this one, to the best of my knowledge, it's not been done. But the point is that this microscopic model that enter the hydrodynamic, the parameter, the constant that enter the hydrodynamic model can be derived from the microscopic parameter that exists in the previous model that we were simulating. Now, these are, most of you have seen Turner two equations, but just let me tell you what they are. They are equations for the density and the equation for the velocity field, which is, in our treatment, is locked to the direction of polarization of this part. Okay, so P you can interpret in this model, in everything I'm going to do, as essentially the speed. Now, what we're going to do is we're going to take these equations, which are highly nonlinear, and we're going to linearize them. Okay? And we're going to linearize them around a steady state, which is the one that we honestly found in the numerics. You can also check that that's the steady state of those equations for that geometry. Okay? So linearize means write the velocity as an excursion from this flow pattern. And also you can linearize in the density. The density doesn't have to be uniform, especially if you squeeze one of these rings to do density waves. It will not be uniform. Okay? And once we've done that, we can derive an equation for the density waves. Okay? So the spectrum of the density waves. Right? Now, to do this, we have to do it in a computer. So imagine if you wanted to study the sound waves in a complicated geometry like that, even for air, you have to put it in console and let it spit the spectrum, which this is a plot of, you can't see the axis, but I have it, frequency versus wave vector. Okay? Now, if the activity is switched off, then this is just the wave equation. The wave equation solved in a very complicated geometry, but the wave equation nonetheless. And these are the bands, okay, that you have in this periodic structure. So you solve it under periodic boundary condition. What I'm going to show you here is the peculiar feature of this band structure in the bulk under periodic boundary condition that gives rise, once you open up an edge, to the very funny topological edge modes. So, first of all, notice one thing here, that there is here the two bands join, they meet. Now we're going to study what happens if you switch on activity. If you switch on activity, the equations are no longer the equations from before, but there is something that looks like a gauge field, if you like, or an extra term in the wave equation. And this term is proportional to the velocity field that you have in the lattice. Okay, now it's you can replot the spectrum in the presence of the spontaneous flow. And you will notice one thing that happens here, is that these bands are now no longer joining, but they've opened up a gap. What does it mean? It means that if you were in the bulk and you try to excite waves at this frequency, you will find none. Okay? Now, in order to create a gap, it's necessary that this vector potential, like in electromagnetism, has some peculiar properties. So in electromagnetism, the vector potential, if you take the curl, it gives you the magnetic field. So if you want a non-zero magnetic field, the curl must be non-vanishing. Now here, this gauge field, I'm drawing some analogies, is the velocity field. So if you take the curl of it and you want it to be non-vanishing over a unit cell, you're talking about having a non-vanishing vorticity, or more precisely, non-vanishing circulation. That is why we had to pick up the Lieb lattice. Because notice in the Lieb lattice, there is an odd number of rings. So if there is an odd number of rings, and one is positive, the other is negative, the other is positive, then the total must be of one sign. If we did that, this is a trivial point, but it's incredibly important. If we did this with a square lattice, this would not work. Why? Because in a square lattice, there's an even number. So the total vorticity, the total circulation will be zero. Now, when people tell you about time reversal symmetry, the first thing that you think is t going to minus t. That's alphabet for a metamaterial. Why? Excuse me. Sorry. Because if you flip t going to minus t in this fraction, well, you will flip this arrow, and this arrow. So you flip the circulation at the level of the unit cell. But if the unit cell is symmetric like this, flipping the arrows doesn't mean flipping the net vorticity, because the net vorticity was zero. So in order to find a net vorticity per unit cell, which is equivalent to a net magnetic field in the electronic system, you need to break both the genuine time reversal symmetry and also some spatial symmetries. So this would have not worked on a square lattice, would have not worked on many lattices. Okay? Now if you did it with a simple fluid and then you spin it yourself, then you can do whatever you want. But if you want the active fluid to go in that state automatically, then you have to choose your lattice wisely. But if you do that, you have to do then a second check. This slide is a touch technical and is one of the last ones. Now you have to characterize topologically the bands. Now what that means is that all this magic that you're going to see depends on the fact that there are some topological invariants, like the winding number of a vortex, for example. Now the way this is defined is the following. You have to take the wave vectors corresponding to the spectrum that you divide in one band, for example this, And you have to construct this object by taking some derivative in Q space. Now, this object, once you take the curl of this object, again, curl, and you integrate it over dq1, dq2, you get an integer. This integer is called a Chern number. Now, this Chern number can be 0, and if it's 0, nothing will work here. So you have to make sure that you choose a structure for which the Chern number is different from 0. So this is not going to be any active flow that is going to guarantee that. Now, if you want to know intuitively, there's a limited amount that one can develop intuition in mathematical physics. But if you want to know intuitively why this is an integer, it's because this quantity is like a Gaussian curvature. And when you integrate the Gaussian curvature over a surface, you get something that looks like the Euler characteristic. So this formula is like the formula for the Euler characteristic in momentum space. But once you have arranged these Chern numbers for the bands in the gap to be different from 0, what you can do is you can look in the gap. That means if you make a finite structure, and now you look exactly at this frequency. And if you look exactly at that frequency, which is exactly what was done by William here, what you see here, this is a map not of the flow field, but of the density fluctuations. You see that the density fluctuations are all localized at the edge. This state in the bulk doesn't exist because it's inside the gap. But in this finite structure, there is a concentration of the density wave right at the edge. And why is that? Because the edge, it's a boundary between the system and the vacuum, which are characterized by two different integers, which are these topological numbers. Now, the thing you can do that William was doing here is to put an inclusion. When you put an inclusion, you see that this mode that exists at that frequency will simply go around, immune to the presence of this disorder. And you can have these states also. There's one thing that is very special about doing this with active matter. This is one last thing I'm going to say, is that if you do this with sound, with almost simple fluids, the penetration depth of this edge mode is controlled by the ratio between the speed of sound and the speed of the flow. Now, if you want this penetration depth to be small, so that the edge wave is really localized at the edge, you have to drive your speed of the flow must be very close to the speed of sound. If you have a normal fluid, this is problematic. This is the regime where you have instability, shocks. But if you have an active fluid that breaks Galilean invariance, then setting the speed of the flow, it's a completely different thing from setting the speed of sound. You can even have the speed of the flow to be larger than the speed of sound. So you have an extreme tunability of the system that stems from the fact that this is a system that breaks Galilean invariance. Final thing is that this edge mode doesn't have to be at the edge only. It can even be inside the system. What I've arranged here, it's a domain wall between material with different Chern numbers. And the only place where the sound wave can propagate is exactly along this domain wall. So this is a way of patterning in a topologically robust way acoustic waveguides. Now, this is my conclusion, and I sincerely hope that this is an example in which we showed how you can take an active media or active fluid, and in the spirit of what the provost was doing today, use them to do engineering. But then you ask the question, what properties are peculiar, or at least much easier to realize in active media than there would be in normal materials? And the answer is, if you want to engineer time reversal symmetry breaking, active matter will deliver it to you for free. Thank you very much for your attention.
Because I didn't say my name this morning. University of Illinois. So there's a lot of talk about down-gap materials being engineered from disordered systems. I mean, these systems are still, they're self-assembled, but they still have very careful geometry in a sense.
Yeah, but you can also actually make them disordered,
so,
provided there are some, no, it actually works pretty much the same, provided that the gap is still there. Now, the problem is that the analysis, actually this whole subject is a bit strange, because the way you do it is you do an analysis in band theory, which assumes that things are uniform, But all the funny stuff, or the interesting stuff, happens when there are inhomogeneities. So actually one of my specialty, which is a touch more complicated than what I described, is to describe those inhomogeneities explicitly by working in real space and avoiding that step. But the point is that this would work also if there's disorder. Now there are some things that you're not allowed to do. For example, if you switch the lattice to that square lattice, it would not work. But in the language of topological insulator, you would say that you made a modification to your material that is not allowed because you no longer have time reversal symmetry break. The other thing that you could do, which is more peculiar to active matter, is that imagine that you had chosen a triangular lattice. But that's a particularly stupid choice because of the frustration. So there's some limit, but within that limit, the imperfection can be tolerated. And actually, you use imperfection, like in the domain world, to localize robustness. But the problem is that this ring could be clogged, then it would just go around. That's the point. That's the robustness that people are excited about.
So I'm Sofia Romano from UCSD. So in the experiment, you have neck in between the rings. You have like small necks in between the ring that join the ring.
Yes, yes.
So you don't have that in the theory. Would that matter? Like, would it change like a time lag that like change something, or like the amount of coupling between two rings?
Yeah. So
or it doesn't matter?
It doesn't matter very much. Essentially, as long as the coupling between the rings is such that it gives you these antiferromagnetic things, then the question that you would have to do, which is even more substantial, is that this experiment here is done with a microscopic model, which is not exactly what we simulated. But most crucially, when you coarse grain this model, it's not a simple toner tube. So you would have to repeat the analysis and make sure that in this structure you have all the features you want. But the details of the coupling between the rings is not so important, as long as it's antiferromagnetic. And if it's ferromagnetic, you just do something different. The problem is that you have to adjust the problem depending on the flow.
Okay, one last question.
Yeah, so you made a comparison with the gyroscopic system, and there you can tune the chirality of the edge mode by changing the lattice. You go from the Kagome to the other, the concave cells. So can you do something similar here apart from
Absolutely.
Okay.
As a matter of fact, the last slide when I showed you the domain wall was exactly an example of that.
Okay.
There I didn't even need to change the lattice dramatically. I just essentially glued two lattices with opposite rotations. By just sliding two of them, and then you have essentially locally a square lattice where the gap must be closed, and then you do the trick. But then you can also do other lattice geometry. Yeah, absolutely.
Okay, let's conclude the order.
Thank you very much.
Okay, our next speaker is Rastko Sknepnek from University of Dundee.
Everybody can hear me, okay? Well, good afternoon. Let me start by thanking the organizers for inviting me to this great conference. So my name is Rastko Sknepnek, and I'm sitting on two chairs at the School of Life Sciences at School of Science and Engineering at the University of Dundee. If you're wondering where Dundee is, well, 57 degrees north, roughly on the level of Anchorage, Alaska, some 30 miles north from Edinburgh. And what is worth seeing in Dundee is RRS Discovery. This is the last wooden ship which was built in the UK, and it was the first British ship that went to explore Antarctica. And now it's built in Dundee, so that's why it's now permanently stationed in Dundee. Okay, so I'm gonna tell you today about our recent work, mainly with Silke Henkes, who is sitting here in the first row, on trying to understand what happens if you put active particles onto a curved surface. And by curved surface, I'm going to mean exclusively spherical surface. It becomes interesting when you do it on the other surface as well. So I'm going to start by first talking about probably the simplest system, which is the polar active matter on a sphere. Then I'm going to continue to the first one is published and the second two are not, on trying to understand what happens if you put nematic particles that nematically order, onto surface. That's done together with Silke and Christina. And finally, I'm going to extend this to trying to understand what happens if you have active polymers that are living, well, in this case on a plane, because it's going to become clear why on the plane. We wanted to start to study polymers on a sphere, but then we realized that actually very little is known about what the collection of active polymers is doing on a plane. So we decided to do this, and that was done with my current postdoc, Pratyusha, and also with Silke. So why would we look into active matter on a sphere? Well, I was a postdoc in Syracuse, and I was working with both Mark and Christina, and you work with Mark and Christina, you have to combine geometry and activity, right? Joking aside, there was this beautiful experiment of groups of Andreas Bausch and Zvonimir Jogic at Brandeis. They put the microtubules on a droplet. I think it's a droplet, it's the, oil in water, right? And then they feed the system with kinesin. They had kinesin motors, and then they feed it with ATP, and then these things start moving, and it's quite spectacular. So we started asking the question, what happens if you have actually active matter on a curved space? And that's why essentially this picture is telling you the story of my talk, right? So we firstly want to understand what happens if you have a simple active system on a sphere. This system in here has a nematic order, it's going to become clear in a second why. And then finally these are microtubules, which are extended objects. So that's where the polymer story comes in. So the first part of the story is done together with Silke, who is even more north than me in Aberdeen. That's probably the northmost university, this is the northmost research university in the United Kingdom. So Silke and I, a couple of years ago, started asking the question, what will happen if you put a bunch of active particles onto a spherical surface? So why is this an interesting problem to begin with, right? But if you, there is something called Poincaré's index theorem, which is also colloquially known as the hair-ball theorem, which in lay terms means you cannot comb a ball without having a single ball, without having a bald spot, right? Practically, or more mathematically, this means that if you have a vector field it is impossible to glue a vector field onto a sphere without having at least one point where this vector field is vanishing, right? So if I cannot, so in plane, I can have a vector field, let's say velocity field, where all the vectors are parallel to each other and have a constant magnitude. I cannot glue this onto a surface of a sphere. I cannot have a flow which has a constant magnitude, a velocity of the constant magnitude, which is everywhere constant on the surface of a sphere, right? And this is a topological theorem which goes under the name of Poincaré's theorem, or Hairy-Ball theorem. Our assumption was that if you put active particles that genuinely intrinsically want to move, want to flow, that this thing, Poincaré's theorem, has to kick in very early on, and this is going to have a profound effect onto the actual behavior, to collective behavior of such particles. Right? So we built a model. Okay, I'm sorry, this is the, so there is supposed to be a sphere in here. Okay, which we don't see, unfortunately. So there is a, so what we did, we essentially took a standard agent-based model where we have soft balls, soft squishy balls that are placed on the surface of a sphere of a radius r, where r is significantly larger than the size of the ball. So a little bit of shading in here will tell you that there is a surface of a sphere in here. It's supposed to be semi-transparent sphere in here. And these guys are confined, they are forced to move on the surface of the sphere, and they interact with each other. And how do they interact with each other? They interact with each other through the spatial interactions, which is just soft core repulsion. effectively they are squishy spheres. They kind of feel each other if they overlap, and if they don't touch, they don't feel each other at all. And in addition, each of these spheres has a small arrow inside, a director field, so it's kind of a compass, right? Or if you think of it as a spin. And then these spins talk to each other following the standard dynamics of the XY model. So they see a certain neighborhood, it's all short range, so they see particles which are in the immediate vicinity. Each particle sees the particles that are in immediate vicinity of itself, and then tries to align. And in addition, we have a noise term. So this hat in here is just a fancy notation for saying that the noise is acting in plane, meaning in tangent plane. So particles try to align with everybody around them, but they are a little bit noisily aligned, they're a little bit tipsy. They're trying to kind of move. They are subject to the random noise which is trying to do this, but they're confined to do this in the tangent plane. Right? The key point in here is that all the distances are calculated in the embedding Euclidean space. Right? So when we calculate distances between particles, we don't calculate the geodesic distance. Right? We don't calculate the distance on the surface, but we assume, which is probably physically more realistic, that these particles talk to each other in the three-dimensional embedding space. Right? And then we effectively numerically solve these equations of motion. So how do we do this? Just briefly. We essentially have an iterative procedure where we make, this is a standard thing from molecular dynamics, where we make an unconstrained move and then we project back onto the manifold, onto the sphere. And the statement is that as long as your time step is not ludicrously large, so as long as your particles are not moving too much, you're not making a mistake. Okay. So now let's actually see what's going on in this type of system. So I'm going to work in the dense regime, and it's important. Once I'm going to show you a picture, it's going to become clear why it's important to work in a dense regime. So I'm going to assume that without activity, I have a perfect coverage. I have density of 1 on the sphere. Right? Without activity, sphere is perfectly covered. I'm going to assume that my particles are only a little bit drunk, right? That there is essentially no noise. So it's pretty much almost deterministic. And I'm going to tune the activity, which is the propensity to move, right? The push. And I'm also going to tune the coupling, the strength of the alignment between these small compasses, small vectors that are leading on each particles, right? So everything else is fixed. The only things that are moving is the activity, the drive, and the alignment between neighboring particles. So for a future reference, the unit of time is the friction coefficient divided by epsilon, where epsilon is the strength of the repulsion of between the particles, and this mu is mutility, which is 1 over gamma in Vincenzo-Stokes, right? In the 1 over the friction coefficient. Right? Okay. So to convince you that in plane this is not very spectacular, so we put in here roughly 3,100 particles. Again, density 1 if they are not active. Gave them some push, which in this case is 0.1. Fairly large alignment. They see each other within some radius of interaction, which is 3 times the radius of the particle. And then you let it play. So coloring here is intensity of the velocity, and this yellow vector, which you probably cannot see, that's the direction of the n vector of the alignment, right? Of the director field. So within roughly 50,000 time steps of the simulation, which is roughly 1 tau, everything nicely orders and nicely marches like an army forever. You know, I can play this forever, pretty much nothing happens. So I would claim that in this regime, very low noise, high density, moderately low activity, and reasonably high alignment, this is not very interesting. Right? This is nothing unexpected. However, if I move on, and if I put exactly the same system, same number of particles, same density, onto a sphere, I see completely different pattern. In here, I'll play a movie in a second. So in here, the color is again the intensity of the velocity, where the darkest colors correspond to high velocity and the brightest color responds to essentially no velocity, to zero velocity. Here is the color scale. And the yellow, as before, the yellow arrow actually indicates the direction of the director field. So we see genuinely different pattern, right? So these are exactly the same parameters, same density, same activity, same J, same alignment, strength. So we see that while the planar system is completely aligned and boring, the active system has quite distinct distribution of the velocity inside, and also the N field is doing really a funny thing. And this is again a direct consequence of the Harry-Bolt theorem, which tells me that I cannot have a situation in which I'm going to have all the particles moving at the same velocity. Right? And of course, the natural thing to ask, and this is what happens if I now start playing with the parameters? What happens if I now start driving the system even more? And where we got surprised initially, but then we understood it, and it's actually to be expected. In the beginning, if you drive it very little, what happens? These guys close the poles. They're a bit unhappy because they all of them have the same push, right? All of them want to move with the velocity v naught, but since it's a crowded environment, they cannot. So they are a bit unhappy, but the entire thing is kind of rotating. However, if you start increasing the drive, particles start realizing that actually it might be more beneficial to start climbing on the head of my neighbor, right? So we start opening bald spots. So you trade off, you essentially start paying penalty in terms of the elastic energy. Particles start self-intersecting, start overlapping. But what you gain is that all of them now are closer and closer to their native preferred velocity, which is V naught, which is driving velocity. You have some kind of a frustration where the repulsion wants them to be homogeneously distributed on the surface of the sphere, while the drive wants them to all have the same V naught, which is not compatible with the topology, right? And then here is the movie with with the 10 times larger driving. So we start always from a random configuration, let the system relax. And after a while, this is what you get, right? You get the configuration in which you have big bold spots, so pretty much everything up to Chicago, down to Chicago is bold, and between Chicago and what would be on the other side, like Rio or a little bit more south, is actually occupied densely by the particles, right? Okay, and then you can actually calculate the density profiles. So on the x-axis we are showing this. So this is the equator. Of course, the symmetry is spontaneously broken. You always rotate the system such that it looks like that the North Pole is up. So the center of this graph is the equator, and then we go up and down like north and south. So we see there is quite a bit of the density build-up at the equator, and we have this kind of parabolic type of profiles that are more pronounced as you increase velocity, as you increase driving. So for low driving, there is pretty much no bending, and as you increase the driving, bend becomes more and more prominent, and you have more and more density build up at the equator. And that's exactly the reason why it's actually not very interesting to look into something like Witschek model, which does not have self-repulsion, because what you get, if you don't have self-repulsion, what you get that all the particles end up on the equator, so everybody sits on the top of everybody else, and you have a line which is just circling on the equator. And the same things happen with the pressure. You have a pressure buildup. So can we understand this? So I used to use the analogy with the Coriolis force, but then I was actually somebody pointed out to me that Coriolis force is an inertial force, and there is no inertia in here. This is all over them. But to some extent, one can draw the analogy. So the idea is that the particle in a flat. I always want to move on a geodesic, right? So if nothing else is obstructing me, so particle. Self-propelled particle on a flat space moves on a straight line, which is geodesic, which is trivial. On a sphere, if I have a single self-propelled particle, that particle would pick a great circle and keep on going on that great circle, which is an equator. But now if I have a bunch of particles, they all want to go on a great circle, but certain great circles are not available because other guys are sitting on them. So you are effectively building. Dynamically, you're building a pressure because you have a particle that wants to go on the great circle, but great circles are occupied, so it gets frustrated and it gets pushed towards inside. And we've actually built a simple analytical model which allows to predict the profiles of the density profiles, the train profiles in this system, which actually surprisingly fit quite well with the simulations. Okay, that would be pretty much the story about the polar system. So now, together with Christina, we started asking what is happening if we get this exactly the same system, but we make a make it nematic. And why are we looking into this? Is because if you look into the Jogic and Bausch experiments, these systems behave as nematics. They have a nematic symmetry, and we know that because we have 4 fractional topological defects. We have 4 plus half topological defects in here, right? There are other, so that's the main hint that this is a nematic system, right? So in the previous case, we had a polar order parameter, right? Polar, our director field was polar, so we could only have integer topological defects. So what we did, we took our model and now try to make it nematic. Again, there is a sphere in here, exactly the same setup. So nothing happened in terms of the spatial interactions between particles, but now things changed in terms of the alignment between particles. So instead of aligning polarly, where this is different than this, now in the nematic case, this and this is exactly the same. And one can actually write this in a vector form. It's important for us to be able to write in a vector form because we are living on this manifold on the curved space, so that's the only way we can actually treat this efficiently implement this without going into weird local coordinates. However, but if you only do this, actually it turns out that this is not sufficient. Let me briefly pause and go through this in a bit more details, right? So we also had to add this another term. So if you go back a couple of slides, if I go a couple of slides back into our polar case, in our polar case, we only had alignment. I had only n cross n term. In here now suddenly, we have to add a local term which couples velocity, locally couples velocity to the director. And why we needed to do this? Well, we realized after doing a bunch of simulation without this term. So if you think of our system are, in the real space, these are just balls that are soft, no friction, right? And then inside of each ball there is a little compass. But at this level, without this term in here, there is absolutely no coupling between the orientation. So I can smoothly change the orientation of my compass without stirring the system. And this is not the case if you have something which is nematic, if you have an object which is anisotropic, right? If I have an anisotropic object, if I have a bunch of rods, and if a rod tries to change its direction, it is going to start stirring stuff around it, right? If the density is sufficiently large. So, and since our particles are point-like particles, we actually had to hook up a term, or kind of had to add up a term, which exactly couples velocity and which is the spatial property, and the internal property, which is n, and gives us this necessary coupling. Okay. So, what do we expect? So in here, we are going to plot the driving velocity times the radius of the sphere, so number of the defects versus the driving, right? So topology tells us that the total topological charge of a sphere has to be 2, right? So I have to have, no matter what I do, if I put a nematic on a surface of a sphere, I'm always going to have at least 4 1/2 topological defects. I can have like two ones, but in most cases I'm going to have 4 1/2s, even without any activity. If I drive the system, so there is a lengthy story behind this. If you drive the system, then the effectively topological defects become smaller. And once you hit the situation in which the size of the defect becomes smaller than the size of the sphere, you hit what is called the turbulent regime or active turbulence, where you spontaneously start generating new topological defects in the system, and that's happened in very large driving, right? So if you are plotting in here the number of the defects as a function of driving, at very low driving, we see the configuration where we have 4 topological defects in very high driving. We have a situation where we have many topological defects. So in here, you see there are these 4 topological defects. They are a little bit dense because this is active, so this is somewhere in here, right? But nothing much happens. However, if you now drive system much higher, you start, whole hell breaks loose, right? And you start getting pairs of topological defects spontaneously being generated in the system. This thing is also followed by relatively large density fluctuations. However, this is not the end of the story. Very interesting stuff happening in between in here, because if you look into this plot, again, there was supposed to be a transparent, semi-transparent rectangle in here. If you look into this region, between the shaded regions, you see that for intermediate values of activity, you suddenly observe a sharp drop in the number of defects, and actually go down to 2 defects. And that's actually very interesting. So, what happens, and Silke really worked hard to map the entire phase diagram. So what happens, you actually discover that there are more, much more, or many more possible states. So for very low driving, nothing pretty much happens, so we just have a standard 4 defect story. However, at the low coupling, at the low alignment strength, if you increase the driving, you transition into a band-like structure, which is exactly the same as it's pretty much the mechanism is very similar to the mechanism of the polar case, right? Where you start having bald spots, which you can interpret as 2 plus 1 topological defects. Again, topological charge has to be 1. Important point, which I forgot to mention, apologize for this, is that there is another time scale in here, because how we implemented that the system is nematic is that we have a time scale over which the direction of the arrow flips, right? So the thing goes a little bit this way and then it flips the other way. If you now push the system even further up in activity, we get this what we call the bending state. So not only that you have bends, but these bends start to bend. So you have a bending bends, right? So you have a bend, and this bend starts bending. I'll show you in the next slide sketch of how this looks like. And now you have like 4-ish topological defects, and this almost looks like it's gonna become turbulent, which it does if you drive it even further. However, if you start moving, it's also interesting what happens if you start moving in this direction, right? So if you're in this bend state and you start increasing the alignment between the strength of the alignment between the particles, we have what is called a merging state, where on the other hand, activity wants the system to align, and wants the system to form bends, but the alignment is so strong. So we're in this regime in here. So the alignment between the particle is so strong that it prefers the 4 topological defects. So you have this constant. You have essentially. You have a situation where 4 topological defects that are normally would be sitting on the corners of a tetrahedron because they repel each other. They come closer to each other, right? They get pushed. They push towards the poles, and you get a situation where they kind of merge and split, right? So you have some kind of transient state where they kind of touch each other and move away from each other. Just a second. So it's really surprisingly rich phase diagram. And then there are a couple of these points, like these, where we could not really decide what's happening, because building this phase diagram involved staring into a bunch of movies, right? So you just kind of run simulations and then determine where you are. Okay, so if you now try to analyze these states, so the key states are the 4 defects, the band state, the folding of the band and turbulence. So we are tracking the position of the defects in here. So this would be, again, a lot is missing. So there should be a grid in here. So this is what the projected polar plot, where we follow the position of the defect. We see there is quite a bit of difference in terms of how these defects, how they evolve with time. So for example, in the bend state, you clearly have a situation where you have only two defects that are slightly jiggling around the stable position. In the tetragonal situation, you have them moving well as more or less as a persistent random walk, and then as you push the driving into the direction of the activity of the high activity where you have turbulence, you pretty much cannot track the defects anymore. They are all over the place. Right? Unfortunately, in the Bausch-Jogic experiments, they've seen this very nice oscillatory pattern of the topological defects, where the topological defects oscillate between the tetragonal position and the planar configuration. So meaning they are sitting on the corners of a tetrahedron, and then slowly evolve into a cross shape in a plane and go back. Unfortunately, we haven't seen this yet in this model. That's something which we need to understand. And so the idea of this bending state might be this again from the Jokic lab. The idea is that maybe what they observe in here is exactly this state which we found. And I promised a sketch. So in this bending state, what happens is you effectively have a bend which now folds as a basketball pattern, right? Okay, so this pretty much sums up or gives a brief overview of what happens if you have a point-like particles with different symmetry. But as you can see in these experiments, these are actually microtubules are quite extended. These are extended objects. These are in tens of microns. So what Pratyusha and I and Silke try to answer is what happens if you now have something extended object. If you have a polymer, and if you have if you have a polymer, and what we did, so we essentially took a recent model which came from a Gompertz group where they studied a single active polymer chain. And this is probably the simplest possible way to model the treadmill type of motion. So you have a standard expression which Vincenzo explained. This is exactly the same equation of motion, except that now our beats are connected, and that our activity is acting tangentially so it's acting along the bond between the beats. So you have a chain, and the activity is always acting such that it wants to push the chain along its contour. Otherwise, it is a regular standard model of the typical coarse-grain simulation of polymer chains. So you have a stretching interaction, you have an angular potential which models the bending interaction. And then you have an excluded volume which is modeled by using the standard Weeks-Chandler-Anderson type of potentials. Right. What is really striking about this system, you can define two quantities. One is the ratio of the passive persistence length. So what is the persistence of the polymer versus the length of the polymer, and the other one is the Peclet number, which is essentially the ratio of the convective and the diffusive, or the ballistic and diffusive. What is interesting is that this is the result of the Gompertz work on a single polymer. As you increase the activity, naively, I was thinking that if you as you increase activity, polymer is going to become stiffer. Actually, completely opposite happens. Polymer becomes softer, meaning the effective persistence lines go down. Polymer starts curling, and you see spiraling like patterns. So polymer curls into a spiral, like a licorice type of thing, and it kind of rotates on its own. So the idea which we had in here, what happens if you have a bunch of such polymers? So this would be a dynamic phase diagram, where on the x-axis I'm going to be showing the activity. So if you go this way, I'm going to increase the Peclet number. I'm going to increase the activity, the push along the contour. And along the y-axis, I'm going to be increasing the passive stiffness of the polymer. Right? So polymer is going to have a passive persistence line which is larger if I go up. I apologize for the quality of this movie. It lost a lot in its quality got lost when I was converting it from Linux to Mac. What is very striking is at low activity, pretty much nothing much happens. What colors mean in here? The color means the different polymer chains. So it's not kind of any type of density gradient. It's just the polymer chains are colored differently. So to identify them. So at low activity, nothing much happens. If polymers are soft and active, there is something interesting going on in here. But up here is very, very interesting stuff. So we see something which looks like, well, I would say maybe motility-induced MIPS, or kind of coexistence phase, where you have a density, large density fluctuations in the system. But what is striking is that these large density fluctuations seem to disappear as you increase the velocity further and further. So what happens in the upper corner of the phase diagram, you transition from these kind of ordered type of swirls into what we call the licorice phase, where now each polymer realizes that actually it is much more favorable to form a more small spiral and swirl its own. So you have a bunch of kind of licorice that are sitting and rotating at the spot. So to the best of my knowledge, this is probably the first example where increasing the activity kills the, maybe I'm wrong, kills the phase separation in the system. And this would be a preliminary phase diagram of this system where we plot the Peclet number. Everything can be scaled, so different symbols represent different system sizes from 5 to 50, meaning different length sizes. And you see four distinct phases, and in here what we call flowing map. This is pretty much a mess. We cannot really decide what is going on. And let me skip over this and essentially summarize. I hope that I convinced you that actually putting active matter onto the curved space is an interesting problem. Putting activity to extending object, meaning polymer-like object, is interesting. And of course, natural thing which I want to do, and it's this next thing, is to actually put polymers onto sphere and see if we can actually get what Zvonimir and Andreas Bausch have seen experimentally. Thank you.
Questions? Yes.
So one of the mechanisms that you mentioned frequently is this Poincaré, what do you call it? No comment here, air and sphere.
Yeah.
And this is a topological statement. There's a second thing that happens, which is even in a small patch, you cannot have two vectors be aligned, because, as you said, the geodesics converge.
Yes. Yeah.
I hear you mentioning that less, but I imagine that that could be just as likely a mechanism for what you see. For example, one thing that I know as a fact, for example, if you take a torus,
Yeah.
in a torus you don't have to have defects.
Yes. Yeah.
But still you have gas.
Yeah.
For example, I know as a fact that if you take an nematic and you put on a surface with non-vanishing curvature, there's an active force which is non-vanishing simply because the curvature on that patch is the difference here. Can you comment on that?
Well, that's actually, thank you for this. This is actually a very good point, right? So probably if I went back to this, probably the most natural thing to first would look into something like Gaussian patch, right? Where you would actually introduce there is, as Vincenzo said, there's a combination of topology and geometry in here, right? So, and it would be interesting to actually detach these two, to actually look into the system where, like, for example, a torus, where topology does not impose any topological defects, but on the other hand, geometry, see if geometry is gonna drive to any.
Well, your model of the sphere has curvature, so even on a little patch, there will be that frustration.
Exactly, yes, yeah. And
that could be responsible. You know, when you say that two geodesics, if one wants to be on one, it cannot be on the other. Aside from that, there's the fact that two of those geodesics will converge.
Yes. Yeah.
And that could be a mechanism to see the things you see.
I think you're right. I think that's actually what is happening, right? Because but I would not comment more on this because I would really want to look into what happens if I get negative curvature, different surfaces that have a kind of varying curvature and so on and so on.
Although you do add it, because some of the things you show on the sphere, that's really a torus, because on the two tops there's no.
There is nothing else, yeah. But again, they cannot do this.
Okay, one more short question.
Well, I just wanted to comment on that and say that, I mean, we've talked about it a couple of times. We can know what happens if you have negative curvature, that there's this geodesic deviation. If the curvature is positive, then the geodesics converge. If it's negative, they diverge, and so you would expect the density to be lower instead.
Density, but also the alignment. The matter, velocity one.
You should need to see all this. Right?
So my name is Kosmrlj. Don't bother figuring out how to pronounce my last name. So just go with Andre. And today I want to tell you how thermal fluctuations affect, mechanics of ribbons. And before we jump into ribbons, I just want to remind you that, for one-dimensional polymers, it is well known that, they're only short on small scales. They're smaller than some characteristic persistent length scales, while on larger scales, they form these random calls, so they basically perform these self-avoiding random walks. And this characteristic persistent length scale is related to the local tangent-tangent correlations and and depends both on the binding stiffness of the polymer and the temperature. On the other hand, if we go to two-dimensional sheets, even in the presence of temperature, two-dimensional sheets remain flat. But again, there's some characteristic length scale, which we call thermal length scale, and above this length scale, thermal fluctuations, effectively, they renormalize elastic constants in this non-trivial power law fashion. And basically what happens is that the bending stiffness is increased, while Young and shear modulus is reduced with these non-trivial power law exponents. And these exponents are the same for all materials, but different materials have these different characteristics thermal length scale. And where does this thermal length scale comes from? You can think of this, like if you calculate what is the amplitude of fluctuations for the given size of the membrane, for the membrane that's of the order of thermal length scale big, then the amplitude of this fluctuation will become of the order of thickness. And that's where thermal fluctuations become important. And if you want to get intuition about these thermal fluctuations, it's also always useful to play with crumpled paper because it provides a very useful analogy. All right, so how are these thermal fluctuations important in two-dimensional systems, right? If you take a regular sheet of paper like here, then this thermal length scale is enormous, and we know that there are no thermal effects in these sheets, right? But if you go to microscopic systems, such as members of cells or bacteria, then you see that the thermal length scale becomes small enough that you may want to think the thermal fluctuations are important. And if you look at the red blood cell under the microscope, you will see that they're flickering. You will think, oh, maybe bacteria are flickering also because thermal length scale is even smaller. But that doesn't happen because bacteria are under huge internal pressure, which is called turgor pressure, and this basically puts this membrane under tension. And if I apply large tension on the sheet, then I'm just going to stretch out all the wrinkles, and then basically the thermal effects are completely suppressed. But now, if I take one of these new two-dimensional materials, such as graphene, then at room temperature, this thermal length scale becomes extremely small. It comes on the order like nanometer. This basically means that we should expect to see like huge thermal effects for graphene sheets as long as they are not under huge tension. And this was indeed recently observed in Paul McKeown's lab at Cornell, where basically they just constructed simple cantilevers with these graphene sheets, and they were just bending them by applying some force with the lasers, or they were just looking at the fluctuations of these graphene cantilevers, which are roughly 10 micron big. And from this you can extract the effective bending stiffness of a graphene sheet. And indeed, like at zero temperature, we would expect to be like the bending stiffness to be roughly 1 kiloelectromoles, but they measured something was 3 orders of magnitude larger. So you can see that thermal fluctuations can indeed have a big effect. And it seems to be consistent with this theoretical picture where we expect to be roughly on the 1 kiloelectron volt, but you also see a big scatter. You see that there's more than a decade in this. And we think that the reason for this is that there are also defects present in graphene, which basically converts graphene in something like a crumpled paper, which also enhances the bending stiffness. And these defects could also give rise to this large scatter. And what happens now if you start playing with graphene sheets and if you start cutting them, then you can get inspired by Kirigami and you can start making soft springs like this. And the reason why this spring is very easy to stretch is because I'm not really stretching material, I'm just locally bending it and twisting it. And you can do the same thing with graphene and the microscale. And what is a cool thing about it, what they showed in this paper, is that once you're stretching these soft springs, you're not really affecting electronic properties. So you can basically use such devices to make microscale flexible electronics or even very sensitive force sensors. But if you want to understand mechanics of these structures, well, you better take into account thermal fluctuations, as I showed you on the previous slide. And if you look at these structures, they will look to you like a bunch of connected ribbons. And that was the motivation why we started to study ribbons. So, okay, I kind of quickly glanced over what happens for one-dimensional polymers and two-dimensional sheets. But what happens for ribbons, right? So the effect of these internal fluctuations inside the ribbon, can be captured naively if we, kind of coarse-grain this ribbon, and we imagine that this ribbon is constructed with these like square blocks of the size of the width of the ribbon, and they just stitch one to each other. Then the effect of these thermal fluctuations are effectively going to be to renormalize these elastic constants inside each block. So we're going to have enhanced bending rigidity while reducing Young's modulus. And then we can just stitch them all together to get like an effective 1D ribbon, which has like basically, and if we ignore the stretching of the ribbon backbone, which is hard, we basically have three easy deformation modes. One is bending in this direction, which is very easy, and it's just associated with this renormalized bending stiffness. Bending in the other direction is very hard because I would have to stretch the ribbon, and that's why we have this renormalized Young's modulus. But twisting is also very easy, as you can play with belts. So twisting is very easy, and it's also associated with local bending. So again, we have this renormalized bending stiffness. And once I have like this effective bending and twisting rigidities, this just now is translated to an effective one-dimensional problem. So we get back to the our usual polymer statistics, where just now they are highly anisotropic because bending in different directions is different. So in order to test this, we connected with Rastko Sknepnek, who just gave a talk, and Mark Bowick to do some numerical simulations. And here you're just seeing some molecular dynamic simulations of these ribbons. And we're going to measure two different things. We're going to attach one side, and we're just going to measure this height fluctuation as a function of distance s along the ribbon backbone. This is going to be one measure. And we're also going to measure this effective persistent length by defining local tangents. We're just going to look at the correlations between local tangents, which are going to define as this persistent length. And we expect that because persistent length is related to this renormalized bending rigidity inside on the scale of the width of the ribbon, we should start seeing this non-trivial scaling of the persistent length, which is different from the polymers, where this would be just doubly divided by t. Is a simple linear power. Okay, so let's first start with this measure. So here I'm plotting these height fluctuations of function of distance, and I normalize them with the R measured persistent length. And now you see these different data points are for a bunch of ribbons that have different width and lengths, and they all collapse on a single master curve, which I can just obtain by treating, like these non-symmetric polymers. And you see that there are two regimes. If this S, distance from the anchor point is much smaller than persistent length, then this behaves basically like a solid, just like a ruler. So it's just like a fluctuating ruler. But once we go, so this is this first regime. But once the ribbon becomes much longer than persistent length, then transitions into this random walking regime, and we get this new scaling approach. So we can also now go back. So from this measured persistent length, we can also try to back out these effective and normalized bending rigidity because they are related to each other. And now if you do again test ribbons of different widths and lengths and temperatures, you again get a nice data collapse. And what you see that this effective and normalized bending rigidity is basically unchanged when the width is smaller than thermal length scale. Like I said, thermal fluctuations only become important on scales larger than thermal length scale. But once the width of the ribbon becomes larger than thermal length scale, then we start seeing transition in this new regime that is basically characteristic of two-dimensional sheets with this exponent of roughly 0.8. So it worked well in numerical simulations. At least in principle, this could also be tested in experiments. I already showed you the results of the bending experiment. You could easily also do pooling by applying gravity or just by applying magnetic forces on these probes, which can also be used to twist these ribbons. And this way we could test that indeed bending and twisting rigidities are normalized in a non-trivial way as a function of this width of the ribbon. Well, at least at this scale, at the 10 micron, it will be very hard to actually probe the semi-flexible polymer regime because the persistent length for 10 micron wide ribbons is on your meters, right? So it's huge. But if you want to get to more realistic scales, you would have to really make nanoribbons, which would only be like a few nanometers wide, and then the persistent length only becomes only a few microns. So if you make these nanoribbons, then you may also be able to see this semi-flexible region. So to summarize, I hope I showed you that like these ribbons are interesting creatures which behave both like 1D flexible polymers, but they also know that they are two-dimensional. They retain some feature of two-dimensional sheets. Namely, this results in this enhanced and interestingly scaled width-dependent bending and twisting rigidities with these non-usual powers. And the one thing that I didn't talk about is, you also get interesting nonlinear stretching of the ribbon backbone, which is also characteristic of these thin sheets. So finally, let me acknowledge my former advisor, David Nelson, Paul McEwan's group for providing me these nice graphene movies and also for inspiration, and also Mark Bowen and Rastko Sknepnek for help with these simulations. Thank you.
Okay, questions? So I have a question. So now the ribbons and sheets you're looking at have a ground state that is flat,
Yes.
zero temperature.
Yeah.
Do you think that a case where it has an intrinsic tendency to twist or to curl up,
Yeah.
so then what happens when you turn off the flat case?
So we haven't looked at that yet. What I have looked at is, instead of taking flat sheets, taking the spherical shells. And what happens is, here the thermal fluctuations, if you put sheets under tension, you can suppress them, but thermal fluctuations effectively don't change the surface tension. But what happens on a spherical shell is that thermal fluctuations effectively produce negative surface tension, which is equivalent to applying external pressure. So even if you have if you match pressure between the inside and outside, thermal fluctuations are going to generate effective pressure. This means that the large spherical shells can get spontaneously crushed at very large temperatures, or if they are big enough. So geometry definitely matters, and it would be interesting to also apply it, to these ribbons, twisted ribbons, helicoids, or stuff like that. Also, in this kind of now active materials that that can be transformed by local swelling or something, which people are now making on a smaller and smaller scale. So at some point we're going to hit the thermal limit, and it's going to be interesting to see what happens there. Yeah.
Zichen from Dramas. So you mentioned about nanoribbons. So do you plan on looking into those real nanoribbons and see, the effects there?
Well, I tried to talk to some people who can grow these nanoribbons. They said that it's when they grow them because why they get nanoribbons is because there's an anisotropic growth on a substrate.
Mm-hmm.
But what I mentioned that this aspect ratio still has to be quite huge. It has to be 1 to 1,000. Whereas experimentally when they're really growing at different rates, they can probably get an aspect ratio of 1 to 10. So just by growing, it will be hard to get. But maybe by lithography, by these maps, you can actually generate it.
And does the mechanical property matter in your study?
Mechanical property of the material itself?
Yeah, right.
Well, the material is going to just affect this thermal length scale, as it is going to the temperature. But once you set this thermal length scale, then the rest is just the rest is just dependence of the geometrical properties. Whether the geometrical length scales are larger or smaller than this thermal length scale, and that's all that matters.
Okay, if no more questions, let's take the coffee break. Please remember to come back at 3:55.